All right, so we've just started talking about these things called relations and these things that are related to a relation called domain and range. What we'd like to be able to do, just like we did with sets of normal numbers, is somehow use a rule of some kind to define a set of relations, okay, or a set of ordered pairs rather. So let's have a look at an example where we can do that. Now, sometimes you can't. Sometimes there is no relationship between the x and y coordinates, so you can't write a rule to define it. You just have to list out the ordered pairs one by one. Okay, but for something like the following, where we've got a set, let's call it B, or a relation, and we'll give it the following ordered pairs: 1, 2, 2, 3. 3, 4, and 4, 5. Now, can you see a pattern between the x and y variables of these ordered pairs? All right, you should be able to see that the y coordinate is just the x coordinate plus one more. All right, so another way that we can actually write this relation in the form of some kind of rule would be to write the following. Okay, so this relation, or this set B, consists of ordered pairs, x comma y, such that the y coordinate is just equal to the x coordinate plus one more. Okay. Now what we also have to do is state which x values we'd like to have our relation defined for. Okay, look at the numbers of the x values in the top statement of the relation. We've got 1, 2, 3, and 4. Okay, there are no other x values apart from 1, 2, 3, and 4. So we can't just plop any x value we like into this relation to generate the y values. We have to specify that we only want x being equal to 1, 2, 3, or 4. Okay. Now, there's actually another way to write this last part of this statement. Okay, we could have written that as saying x could be any number that belongs to the set containing 1, 2, 3, or 4. Okay, so this here is equivalent to this here. All right, whichever one you want to use is up to you. You'll see that it's going to be more easy to write it in terms of set notation rather than just listing out what x could be equal to. Right, so we'll see that in another example here. So let's define a very similar relation where we're going to have the relation called C being equal to the ordered pairs. Let's say 1, 2, 2, 3, 3, 4, 4, 5, and so on and so on. Okay, I haven't stopped writing. Okay, I could keep writing these ordered pairs if I wanted to. And in fact, this relation contains an infinite amount of ordered pairs, infinite amount of coordinates. So how could we write this? How could we explain this list to somebody using maths notation? Okay, just in the same way that we wrote out this other way of describing relation B. Well, again, look at the relationship between the x and y coordinates. Okay, it's very clear that you can just get the y coordinate by adding 1 to the x coordinates, exactly the same as the one in relation B. Okay, so we could start off by saying C is the set of ordered pairs x and y such that the y coordinate of the ordered pair is just going to be equal to the x coordinate plus 1. All right, now just like we did for B, we have to specify which x values we are using to generate these ordered pairs. Okay, so this rule here, y equals x plus 1, this will generate the y values based on an x value. Okay, now we can't just use any x value. Look at my relation. I've got 1, 2, 3, 4, and then it would continue with 5, 6, 7, 8, and you can see they're all positive whole numbers. All right. Now, thinking back to our sets, is there a way that we could write down all the positive whole numbers in a very small statement? Why, yes, there is. Okay, we are talking about the natural numbers. So in this relation, we are specifying that x must be a natural number in order for this relation to sort of work out. Okay, it's not allowed to be things like 1.1 or 2.7 or something irrational like the square root of 2. It has to be a positive whole number. And that's what this last part here is saying. Okay, it's a qualification. All right, so there we go. That's another way to write out the rule of a particular kind of relation. Let's do one more, again, closely related. Okay, so let's say I've got something like some relation D, where I've got some ordered pairs. I'm just going to write a bunch down in no particular order. Okay, 0, 1. We could also have 0.1, 1.1. Or we could also have 0.01, 1.01. Okay, and I can continue this kind of pattern until you get to 1, 2. Then I could keep going and say 1.1, 2.1, or 1.01, 2.01. Okay, and I could keep going with that pattern. And then I could throw some other types of coordinates in there. I could say something like square root of 2 and square root of 2 plus 1. Okay, that's a coordinate, or a set of coordinates, right? And I could do a bunch of rational numbers like irrational numbers like that. Okay, I could also do negative numbers. All right, let's say I've got some negative x values in here. Let's say negative pi. All right, and the y value would be negative pi plus 1. All right, or I could have something like negative 9.823, and the y value would be negative 8.823. Okay, and I could just continue writing out a whole bunch of different types of ordered pairs, different types of coordinates. Now notice, I'm trying to get you to see here that x could be any value you can think of. We're not restricted to whole numbers. We're not restricted to positive whole numbers. We're not restricted to rational numbers. It could be irrational. It could be any number you like as your x coordinate, okay? But also notice the relationship between the x and y coordinates, okay? The y coordinate is still just being obtained by adding 1 to the x coordinate, okay? So the rule, at least this part of the rule, is still the same, okay? It's still going to be y equals x plus 1. So our set D is all the ordered pairs such that the y coordinate is equal to 1 plus the x coordinate. But here, x can be anything you like, okay? Any number you choose, all right? And we can be confident that any number we choose for x, there's going to be a corresponding value for y, okay? Just based on the equation that we've got here. Just add 1 to it. Now, if we can choose any value for x, okay, what set of numbers does your x value belong to? Well, just like the positive whole numbers are called the natural numbers, the set of any possible number is the real numbers. Okay, so we could just say that x is an element of the set of real numbers. X could be anything that you like. All right. Cool, so there we go. That's how we can describe sets, and in particular sets of infinite ordered pairs, such as in C and D, with some rules and some qualifications for what x is allowed to be. All right. Now, just quickly, what we'd also like to be able to do is write down the domains and ranges of these particular relations. So let's go back and look at B. All right. So let's write down the domain and range for B. So the domain of B. Okay, now remember, the domain of a relation is just the set of all the x coordinates of that relation. So if you look at the x coordinates in the first statement here, we've just got 1, 2, 3, and 4. Pretty straightforward. But notice this set here is equivalent to the way that we've written this set here. Okay, so this part of your relation rule tells you what the domain is. Okay, so the domain for relation B is just 1, 2, 3, and 4, because that's what that part there says. It tells you what x is allowed to be, basically. All right. Now the range of B, well, again, you have to sort of look at your ordered pairs in your set, and you just list out the y values. So we've got 2, 3, 4, and 5. Okay. Now that's pretty easy to do if you have a list in front of you of what all your ordered pairs are. You just look at the x or y values and write them down in a list. But for things like C and D, where we don't have the entire list in front of us, we've only got a rule that's generating the ordered pairs in our lists, in our sets, then things are going to be a bit trickier. Okay, but at least we've got this part here. Okay, that part there tells you the domain. That part there for D tells you the domain of D. So writing the domain out is generally pretty easy if we've got our relation written in this way. So the domain of C is just natural numbers. Easy. All right, what's the domain of D? Well, x could be any real number. So the domain of D is just the real numbers. Cool. Let's think about the range of C. All right, so if you look at the way that we've started writing out our relation for C up here, we've got 2, 3, 4, 5, and it would continue with 6, 7, 8, and 9. Okay, those are the y values, and it goes all the way up to positive infinity. All right, now that's very close to the natural numbers. Okay, but the natural numbers also include the number 1, which our range doesn't seem to include. It starts at 2 and goes from there. So one way that you could write that down is you could say that the range of C is the set of all natural numbers except for the number 1. Okay, that is not included in our range. All right, and that's a perfectly acceptable way to write the range of C. All right, what else have we got? So the range of D, well, that one's a little bit trickier to sort of give an argument for. You just sort of have to be able to see that the range of D is also any real number. Okay, and why is that? Well, I'll give you a reason in the next video. But basically, if x can be any real number, and any of those x values will give you a corresponding y value, then it sort of translates into the fact that y is also going to be any real number that's possible. There are infinitely many real numbers, each of which can be translated to a y value. Therefore, there are infinitely many y values which are all also real numbers. Okay, so that's a bit of a wishy-washy argument, but we'll see in the next video that there's another way to sort of describe or talk about or think about what the domains and ranges of our relations are. Okay, so we'll stop it there. All right. Now, just quickly, before you go watch the next video, let's have a look at our domains and ranges of all of these things that we've got. And so for relation B, we've got a finite amount of numbers in our domain. We've got a finite amount of numbers in our range. Okay, and the actual amount of numbers in each of the domain and range, that's the same. All right, interesting. For C, we've got the domain of C being all natural numbers. That's an infinitely large amount of numbers. And the range of C is also an infinitely large amount of numbers. If you take away 1 from infinity, you're still left with infinitely many things. Okay, so both of those are infinitely large. What about D? Well, both of them are real numbers. So both of them, again, are infinitely large sets of numbers. So here's a question. Is that always going to be the case? Okay, if your domain is a finite set of numbers, does that mean your range will be a finite set of numbers? Can your domain be finite but your range be infinite, or vice versa? Okay, have a think about it, play around with it, and see what you can come up with. All right, we'll stop there. See you later.